Rational means numbers that can be written as a fraction. Another way to write a radical expression, so we've been dealing with radicals, is to write it in exponential form using rational numbers. And so the first example we're going to do is we are just going to deal with numbers to a fraction. And then we're going to talk about converting back and forth. All right? So you'll notice that when it has something like the square root, it is to the 1/2. When it has the cubed root, it's the same as to the 1/3. And when it has the fourth root, it is to the 1/4. So you should see a pattern there. The fraction represents the radical. Square root is represented this way, cubed root, fourth root, etc. All right? And so again, you are looking for the principal root of these. So if you look at the first example, simplify the expressions. 125 to the 1/3. Then they have 5 to the 1/2 times 5 to the 1/2, 10 to the 1/3, 100 to the 1/3. And so the first one is there's no multiplication involved. So you just, a rational exponent doesn't really make as much sense in our brains. Something to the 1/3 does not make as much sense as the cubed root of something. And so the first thing we're going to do is say, what's the easiest way to handle this particular problem? For this one, I would rewrite it. The 1/3 indicates the cubed root. And so now that I have this, if you don't know the cubed root, you can use your factor tree. If you do know, you can go straight to it. All right, so I'm looking for something that repeats itself 3 times. The cubed root of 125 is 5. So that means 125 to the 1/3 equals 5. All right, 125 to the 1/3 equals 5 because 5 is the cubed root of 125. Now, the next one, I don't have a square root of 5. I just don't have one. And so converting it to radical form may not be the easiest mode here. But what I do know is I have the same bases. I have the same exact bases. So if I were to rewrite this, that would be the square root of 5. If I were to rewrite this, that would be the square root of 5, right? And so I now have the square root of 5 times the square root of 5. What's the rule there? When I multiply square roots by themselves, I just get what's inside. The reason I get what is inside is because this will multiply to the square root of 25, which is 5, all right? And so for that one, the multiplication is going to help me there. Look at this last one. This last one, cubed root then. Something to the 1/3 is the cubed root. Cubed root of 10, cubed root of 100. 10 does not have a cubed root, and neither does 100, but I am multiplying. So I have the cubed root of 1,000. 1,000 does have a cubed root. In fact, if I were to factor this guy, 10 and 10, and then this is 10, you can see the cubed root of 1,000 is going to be what? 10. And so converting those 1/3, 1/2, 1/4 to roots very often will help you very quickly calculate it. So try those 3, A, B, and C. On the first one, 16 to the 1/4. So you are looking for the fourth root of 16 here. So for this one, what should you have gotten? 2. You should have gotten 2. The fourth root of 16 is 2. Make that a little lighter. All right. 2 to the 1/2 times 2 to the 1/2. All right. When you do that one, what should you have gotten there? 2 as well. All right. And then 2 to the 1/2 and 8 to the 1/2. When you multiply those, you would get 16 to the square root of 16, right? Square root of 16. And so what should your answer have been here? 4. All right, so the key concept here at the top of this page says if the nth root of a is a real number and m is an integer, all right? So we have real number roots, meaning we're not taking roots of negative numbers, real number roots. All right, index is real number and exponent is real number. So up until this point, we have just done 1/2, 1/3, 1/4, etc. But what happens when there is an exponent within your root? okay? What happens when there is an exponent within your root, so if you look over here to this second one, you have the nth root of a to the m power. So not only do you have a root, an index, you have a number in here or a variable to a power, all right? In rational form, the exponent is your numerator. The index is your denominator. So for the examples we just did, they were all to the first power, which is why it was 1/2, 1/3, 1/4, etc., right? But when you have a power in there, the numerator is the exponent, the denominator is the index. Now, so we have something to a fraction. We can rewrite it this way. You can calculate it two different ways, all right? So then they show you this other way to write it. Why does this matter? Okay, because sometimes it is easier to take it to the power and then take the root. But sometimes it is easier to take the root first and then take it to a power. It just depends. If I am taking something to a power and then it's going to help me have a perfect root, that's one thing. But if I'm not, I'm just making my numbers bigger before I find the root, okay? And so you can do it either way. You can take it to the power first, and then you can find the root, or you can find the root first and take that answer to the power, all right? It says this, if m is negative, a cannot equal 0. A cannot equal 0. And that's just because negative would put this in the denominator. So a negative number would put this in the denominator, and we know that from our exponential properties that we would have learned in like algebra 1. So this example 2 here, write the exponential expression x to the 3/5 and y to the negative 2.5 in radical form, all right? So we're going to take this first one here, x to the 3/5. So I have x to the 3/5, and they want it in radical form. Radical form's a root, all right? So in radical form, I'm going to have that, and I'm going to have an x. My numerator is the exponent on my x. My denominator is the index of my radical. So that would be in radical form. All right, let's look at the next one. Y to the negative 2.5. Now, negative 2.5, if I'm going to write it in radical form, I need that as a fraction. So 2.5, right, as a fraction. Just to jog your memory here, 2.5 is the same as 2.5, right? If I want that as a fraction, I'm going to multiply and add. So I'm going to have 5 halves. Everybody see that? 5 halves, right? And so if it is negative, so I have y to the negative 5 halves, then that, because it's a negative, puts that in the denominator. Negative exponent puts it in the denominator. So I have 1 over y to the 5 halves. All right, 1 over y to the 5 halves. And then my final step is to convert it to radical form. Radical form. Well, radical form is going to say, I put it as a radical. I have my y in here. The 5 is my exponent. The 2 is my index. Because it's a square root, I don't even have to write the 2. So this would be in radical form. And you can write, like they have in parentheses either way, which is fine. All right? So radical form would look like that. Questions on converting to radical form. Okay. Let's look at B here. So B says write the radical expressions as exponents. There are some times, especially when you have multiple things to multiply, that it is easier to convert it to a rational exponent and do all of your multiplication and then convert it back if you need to. And so there will be times when you want to do it both ways. This first one that we're going to look at is the square root of a cubed. So I have to think about what my index is here. My index for this one is a 2, all right? And if I want to write this in rational exponent instead of radical form, I'm going to say a. The 3 is going to be my numerator, 3. The 2 is going to be my denominator, a to the 3 halves. That would be it in fractional exponent form, rational exponent form. Let's look at the next one. The 5th root of b and the quantity is squared. I'm going to have b here. My numerator is the exponent, 2. My denominator is the index, 5. All right, so check your work on that first one. 1 over 8th root of y cubed, 5th root of z squared. For the second one, write the expressions in exponential form. So for this one, x to the 2/3, y to the 3/2. Y to the 3/2. Let's look at the critical thinking. Refer to the definition of rational exponents. Explain the need for the restriction. If m is negative, a cannot equal 0. We talked about that a little bit, but why, if m is negative, can a not be 0? These are actually properties that we have done before. All right, we did these in Algebra 1. We used them in geometry, and we are reviewing them in Algebra 2. They work for whole number exponents. They work for fractional exponents, okay? They work for all exponents with like bases. So the first one, if you are multiplying like bases, you add the exponents. They give the example, 8 to the 1/3 times 8 to the 2/3 is 8 to the 1/3 plus 2/3. That's 3/3, reduces to 1. 8 to the first power is just 8. All right? If you take a power to a power, you multiply your exponents. They give the example, 5 to the 1/2 to the 4th. That is 5 to the 1/2 times 4. 1/2 times 4 is 2, so that's just 5 squared, or 25. If you have two things in the parentheses, and the whole parentheses is to a power, everything in the parentheses goes to that power. So 4 times 5 to the 1/2 is 4 to the 1/2 times 5 to the 1/2. 4 has a square root, that is 2. 5 does not have a square root, that's why it didn't simplify. Another way to write this would be 2 square root of 5. Anything to a negative exponent is that to the positive exponent in the denominator. And by the way, if you have something in the denominator to a negative exponent, it jumps it up to the numerator. A negative exponent will take it either from the top to the bottom or the bottom to the top, all right? The example, 9 to the 1/2, negative 1/2 is 1 over 9 to the positive 1/2. The square root of 9 is just 3. So 9 to the negative 1/2 is just 1/3. If you are dividing like bases, you subtract their exponents. Pi to the 3/2 over pi to the 1/2 is pi to the 3/2 minus 1/2, which is 2/2, or pi to the first power, which is pi. And then if you have a group and you're raising that group, division works the same way as the multiplication. Everything in the group is taken to the power. 5 over 27, all to the 1/3, is 5 to the 1/3 over 27 to the 1/3. That's the cubed root of 27, so that is 3, and the cubed root of 5 does not reduce. So for this example, it says simplify each number. Simplify each number, all right? They do this a couple of different ways, and they show you both methods here. You are going to use whichever method works the best for you. So for this one, the first thing they do is they take it to a root that you would know. So if you know that 32 is a base 2, then you can rewrite it. My concern with doing it in the first method, so if you look at their first method, they said, oh, well, negative 32, that's just negative 2 to the 5th power. So I'm going to rewrite the negative 32 like that. Most people do not go here first. They don't think, oh, 32 is just 2 to the 5th. Like, that's not where their brain goes when they see the number 32. All right? And so this method requires you to know a lot about your roots and to recognize them easily. If you do, then you can rewrite it, and then you can take that to the 3/5. And then you can use the power to a power. Power to a power means multiply. So that's negative 2 to the 5 times 3/5. Your 5s will cancel, so that is the same thing as negative 2 to the 3rd, which is just negative 8. And so you get this walk around method of doing it. Now, here's the truth. Most people won't recognize that. And so typically when you have something like this, it's easier to rewrite it in radical form. So I would rewrite this, and I would say, well, negative 32 with a fractional exponent is going to be negative 32. That's the 5th root, and I'm going to take that 5th root to the 3rd power. This is what most people would do with this. So once you have this, you can use your factor tree. And then all of a sudden, you'll see that 2 is your base. So you can say 32 is 2 and 16, 2 and 8, 2 and 4, 2 and 2. All right? And I have 1, 2, 3, 4, 5. I am looking for a 5th root. So I know the 5th root of negative 32, it's an odd root, is negative 2. And so then I can take that negative 2 to the third power. So then I just have negative 2 times negative 2 times negative 2, negative 8. That is the method most people would use for this one, all right? Change it to a radical, use your factor tree for the root piece, and then take that answer to whatever power you have it taken to. Let's look at 4 to the negative 3.5. All right, so in this case, you probably will recognize that 4 is a base 2, but you still may not think to rewrite it that way. So if I did the first method, 4, and I rewrote it as 2 squared, all right? And then negative 3.5, I need that as a fraction, all right? I need that as a fraction. However, in this case, I could potentially leave it as a decimal because I have a power to a power. So I have to the negative 3.5. So I have a power to a power, right? So when I do it this way, I can just multiply my 2 and my negative 3.5, right? What is 2 times negative 3.5? Yes, so I have this times this is 2 to the negative 7. Negative puts it in the denominator, so it's 1 over 2 to the 7th, right? 2 to the 7th is just 128, the number I just called off, right? So 1 over 128. That's one method, all right? The other method is to convert this to a fraction, all right? So 3.5 is the same thing as 3.5, right? Which is 7 halves, correct? So far, so good. So I have 4 to the negative 7 halves. So then I'm going to rewrite it as 1 over 4 to the 7 halves, and then I'm going to write it in radical form. 1 over radical form, 4. The denominator is my index, so that's just a square root to the 7th. What's the square root of 4? 2. 1 over 2 to the 7th, which is the same thing I got when I did it the other way. 1 over 2 to the 7th. So both methods work, doing a base and a power to a power, or just converting it to radical form and solving it using your radical. (25) to the negative 3 halves. You could have written that as the square root of 25 cubed in the denominator position. So that would have given you what as your answer here?
5 cubed.
Yes, 1 over 5 cubed, which is 1 over 125. 1 over 5 cubed, which is 1 over 125. For B, 32 to the 3/5, that is the 5th root of 32 cubed. 5th root of 32 is 2, and when you cube it, you get 8. 8. For C, your exponent is not the negative. It is your base, all right? So the 5th root of negative 32 is negative 2. And when you take negative 2 to the 4th power, you get positive 16. Positive 16. All right, let's look at A. All right, for A, I'm going to rewrite this. It's to the negative, so I'm going to put it in the denominator. All right. And then in radical form, the 2 is my index, so that's the square root. I don't really have to write that, but I can. Square root of 25, and that is raised to the 3rd power. So then I take the square root of 25, which is 5, so 1 over 5 cubed. 5 cubed is 125, so I get 1 over 125. All right. For B, 32 to the 3/5, so I'm going to write it in radical form. My index is the 5, so I'm looking for the 5th root of 32, and I'm going to raise that to the 3rd power. All right, so if I do this, I'm going to get 2 and 16, 2 and 8, 2 and 4, 2 and 2. 1, 2, 3, 4, 5. 5. 5th root of 32 is 2. So I have 2 cubed. 2 cubed is 8. All right, so they want us to write this in simplest form. We have 16y to the negative 8 to the negative 3/4. All right, 16y to the negative 8 to the negative 3/4. All right, so the first thing I want to look at is the fact that you have a negative exponent inside and a negative exponent outside. When this happens, you're going to have some jumping around. Like one's going to turn positive, one's not going to be positive, etc. And so when I was doing this one, I would actually look at them individually. I would take 16 to the negative 3/4, and then I would take y to the negative 8 to the negative 3/4. So I would do those individually. So for the first one, I would say 16 to the negative 3/4 times y to the negative 8 to the negative 3/4. All right, and then I'm going to put them together. And so for 16 to the negative 3/4, the negative, it's 16 to the first power, right? 1 times negative 3/4, it's just going to be 16 to the negative 3/4. So that's going to put it in the denominator, 1 over 16 to the 3/4. All right? And then I'll put it in radical form. So 1 over the 4th root of 16, and I'm going to take that and cube it. All right? So then what is the 4th root of 16? Well, if you don't know, you can do your factor tree, but it is 2. 4th root of 16 is 2. And so I'm going to take that 2 and I'm going to cube it. What is 2 cubed? 8. So this piece of it right here is going to change to 1 over 8. That's that first piece. All right, let's look at the second piece. The y to the negative 8 to the negative 3/4. Well, I have to multiply these. I have a power to a power. So I have y to the negative 8 times negative 3/4, and that's 8 over 1. All right, and so this, of course, reduces like this. I have negative 2 times negative 3. What's negative 2 times negative 3? 6. So I have y to the positive 6. That means that this piece of it reduces to y to the 6th power. All right, that is y to the 6th power over 1, by the way. It's in the numerator because it has a positive exponent. So to simplify this whole thing, I am just going to multiply across, right? Multiply across, I get y to the 6th over 8. Y to the 6th over 8. So when you have a group like this and you have a lot of stuff going on, you have to figure out the best way to simplify it. And what typically happens with these is people do nothing with the 16. They leave that 16, and then they simplify the y to the negative 8 piece of it. And so they would end up with 16 y to the 6th, and that's wrong. So you have to make sure every piece within your parentheses gets simplified. So go ahead and try check understanding number 5. So you could have written this whole problem here, this group, since it's to the negative, it could have been 1 over that group to the positive. And then you would have gotten 1 over 16 to the 3/4, 1 over y to the negative 6. And the negative in the denominator would actually pop it to the numerator, and then you would have to simplify this 16 to the 3/4, which stayed in the denominator. Sometimes doing it individually helps. This way you could have actually, neither one's going to change. When I usually do them individually is when one of these is to a negative, and so they're going to do 2 different things when you change them. Because these did 2 different things. One went to the bottom, one stayed on the top. So when you have within it a positive and a negative exponent, then they start moving around differently. And so that's when it's sometimes easier to do it separately. For this one, you should have gotten 1 over 2x to the 5th. 1 over 2x to the 5th. So let's do this one together. So for this one, the whole thing is to a negative 1/3. On the inside, both my 8, that's to a positive 1, and my x is to a positive 15. So you can do them individually, or since they're both to the same positive negative exponent, they're both to a positive exponent, you can shift the whole thing to the denominator. Either way is fine. All right. So if I shift the whole thing, I would say 1 over 8x to the 15th raised to the 1/3. I can do it that way, which would be 1 over, and I'm going to do them individually, 8 to the 1/3. Well, I write that cubed root of 8, right? Times, I have the 15th to the 1/3 for this one. So I'm going to multiply x to the 15 times 1/3. What is 15 times 1/3? 5. So the x becomes x to the 5th. The cubed root of 8 is just 2. Right? Or I could do it individually. I would say 8 to the negative 1/3 and x to the 15 times negative 1/3. And you would end up putting both of those in the denominator. 1 over 8, this cubed root of 8, and then times 1 over x to the 5th. And then you would still get the same answer.